Hello, Honors Chemistry, and welcome to 7.9, where we talk about redox reactions, right? And when we say redox, we mean oxidation and reduction, right? As in, both of these things are happening, right? Your book gives you that little memorization tool, right? That says oxidation is a loss of electrons, right? So oxidation is a loss of electrons, right? Reduction is a gain of electrons, right? And really that would only be helpful if we were assigning oxidation states, which we're not going to bother with now. I think that happens somewhere like chapter 19 or something like that later in the book. And that's really beyond what we need to know, right? What we're trying to do is we are just trying to assess what happens when I put two reactants in proximity to one another. What happens, right? And that's where we are right now, okay? So how do we recognize that something is a redox process if we're not going to assign oxidation states? And there are going to be there's one huge clue, right? And that huge clue is the presence of an element, right? An element as a reactant, yes? And it has to be an element, right? And if we think back to elements, those are the things on the periodic table, right? And don't forget that some of those are diatomic, right? So if we have a diatomic element, that's still an element, right? It doesn't need to be an atom. It just needs to be an element, right? And if we look at this first one, right, we've got two elements, right? We've got hydrogen and oxygen, right? If we look at this one, we've got two elements. If we look here, right, we have one element, but again, it still meets the criteria that there's an element on the reactant side, right? Here, again, two elements, and again, two elements, right? And if we think about what that means, right, so we're not going to assign oxidation states formally, right? But if something is an element, right, that means that it's in its natural state, right? It's in terms of, and when we talk about oxidation states, what we mean is the sharing of electrons, right? Are they sharing equally? Are they sharing unequally, right? And if something's an element, right, it is sharing in whatever is the natural way for it to share as an atom, right? When it combines with something else, right, the odds are that sharing is no longer equal, right, which means that something has more access to those electrons and something has less access to those electrons, which is, again, the give and take, right, loss of electrons or gain of electrons. So, anyway, we should recognize that all these qualify as redox because there is an element as a reactant, okay? Now, let's talk about how you would be able to predict the products, right? So redox, is a whole range of reactions, and again, we're going to keep our range very relatively narrow. But if we look at a lot of these, any of these with two elements, right? How do we define an element? Right, an element is the simplest building block, right? It is the simplest form, right? Everything is composed of one type of atom or in a diatomic, one type of molecule, right? Which means that for a chemical reaction, there is only one option. If we have two elements on the reactant side, they will produce one new compound, yes? Like that's the only option, because from elements, all we can do is build a compound. There is no rearranging that we can do because there aren't any cations to switch, right? There is nothing else we can do. So if we look here, hydrogen and oxygen make water, right? Iron and oxygen make iron oxide, which is rust, okay? And note that iron oxide, I would have to tell you the charge of iron, right? But it's a formula that's worked out based on chapter 5 rules, right? Sodium and chlorine make, oh my gosh, sodium chloride based on chapter 5 rules, right? The fact that sodium is a +1, right? Chloride is a -1, so there's one of each. Sodium and oxygen make, oh my gosh, sodium oxide, again, based on those rules, right? And that sodium is +1, oxygen is -2, and so we need two sodiums in there to make that formula correct, right? So again, two elements will just make one new compound, okay? This does double duty as a redox / combustion reaction, which we'll talk about momentarily, right? But I do want to emphasize the elements part, right? The only option for elements is to put them together to make a new compound, okay? And then we have our combustion reactions. So, which of these are redox? So we're looking for those same clues. Do we have an element here? Indeed, we have two, so this is redox. Here, do we have an element? Absolutely, this is redox. Now, this might seem a little bit confusing to just have ions because we've talked about before, ions don't just run around by themselves, but this is aqueous, right? And so really what this is giving you is this is a net ionic, right? It's a different way to write a net ionic, right? In that this tin is actually a part of something, right? So it could be SnNO3, 2, right? Or it could be SnCl2. Could be any of those things. But the point is that other thing is a spectator ion and doesn't participate in the reaction, so it's giving you a net ionic, right? So just to clarify, right, those tin ions don't exist by themselves, right? Just whatever it was attached to is not important in the scope of the reaction. Okay, next one. Do we have an element on the reactant side? No, so not a redox. Do we have elements? Yes, that one is a redox. Good, makes sense? All right. Next up, combustion, special kind of redox. So your book only lists combustion as a special type of redox because these are the reactions that power like most everything, right? And since most of you guys are drivers, right, going back to life things we should know, right, the vast majority of us still have internal combustion engines, right, which means that we take some octane, which actually is mixed with some ethanol, right, so octane, oct meaning 8, right, so C8H18, right, liquid form, which again, you should know because I mean, I guess if you're learning how to drive, right, you should know how to pump gas, right, which then will react with some oxygen gas, right, to produce CO2 and H2O, right? Ethanol, which is one of those additives in gasoline, so if you pay attention to the signage at the gas station, it says that it's up to 10% ethanol, which is supposed to help with the decrease the amount of carbon dioxide that it produces, right? So ethanol is C2H5OH, right? Also a liquid plus oxygen, oh my gosh, is also going to give us CO2 and H2O. In this case, water is going to be a gas, right? And again, that goes back to the fact that this is a combustion reaction, right? And large amounts of heat are produced, right? And so we'll see here, right, going back to what's in your book and what's in your outline, right? If a compound is composed of C and H, right, C and H or CHO, it's always going to react with oxygen via combustion and produce these things, right? Now, these reactions are very exothermic, but obviously they don't just happen on their own. Yes, does that make sense, right? We have octane sitting in our car and oxygen, and they sit there all day just fine, right? They don't combust until we input some energy, right, via a spark, right? Which is why in our engines, right, we actually have something that creates a small spark, which then creates a controlled combustion reaction. That combustion reaction, the heat, then makes the gases expand, right? And as that gas expands and then contracts, right, that's what then moves all your bits and pieces, which then move your axles, which then move your tires, right? And obviously, since it releases so much heat, a lot of our energy get lost as heat, right? Which is why internal combustion engines, while they provide a great amount of power and a relatively affordable fuel source, right, are terribly inefficient, yes? Which is one of the, if you read the advertising for battery-powered cars, right, one of their key selling points, right, is that the process is much more efficient than it is for a combustion engine, right? More of the energy you put in actually goes to power your car. Okay, so then that brings us to how do we write a combustion reaction? Well, we just did it, right? So pentane, no, I don't expect you to know the formula for pentane, right? But that would be C5H12, and it's a liquid. O2, you should definitely know that's a gas. What's it going to make? Oh, we have a carbon-hydrogen compound known as a hydrocarbon. And we have some oxygen, and that's going to make, CO2 and H2O gas, right? And down here it says liquid propanol. Propanol, that's C3H7OH, liquid, plus O2 gas. Oh my gosh, carbon, hydrogen, oxygen. That's going to be CO2 plus H2O. Nope, this is going to be a gas. Okay, so then now all we've got to do is think about how to balance these, right? And we'll do just like we did previously, right? So C5, 5 here, 12 would mean a 6 here, which gives us 10 plus 6, which is 16, which gives us an 8 there, and we would be done, right? Okay, and then so balancing this next one, right? So we have C3H7OH, right? So sometimes when the hydrogens are split, it's easier to just go ahead and rewrite it, right? So we could rewrite this as C3H8O, right? And that's just going to make it easier for us to look at and focus on our math, right? So we would put a 3 here, and we would put a 4 here, which would give us 6 plus 4, which gives us a total of 10 oxygens, right? But if we have to take 1 oxygen here and then the 2 oxygens here, there's no way for us to get 10 out of that, right? by just putting a coefficient here anyway. So what we're going to have to do, right, is we're going to have to put a coefficient in front of this, right? So now that we have that, let's try again, right? So now we'd put a 6 here and an 8 here, and then we would have now 12 plus 8. 12 plus 8 gives us 20, right? And then we'd have to subtract off the 2 from here, right? Subtract off that 2, which is then means we have to get 18 out of here, which means we'll put a 9 there. Yes, does that make sense? And then we will be done. All right. Thank you for listening. Be good, and I'll see you in the next video for a summary and wrap up of Chapter 7. All right. Be good. Bye.